I'm going to be the second speaker, so just little warning. I actually learned yesterday that I was talking today, so I don't have a lot of slides, but I have some code. And I've been doing that, for a while, thinking about that stuff, working on another project, and I would like to revisit the visitor pattern with you. So first, my question would be, who here already knows the visitor pattern in a way that you are comfortable explaining it to other people? Okay, so that's not a lot of people. So that's interesting. So basically, I will redo everything from the beginning. So actually, the slides are meaningless, and everything is in the GitHub repository, and we go through all the examples. So it's really a story that I'm going to tell you today. So first of all, we're going to go through the visitor pattern. As it's actually introduced in the book Design Pattern from the Gang of Four, which was actually written at a time when you didn't really have you didn't have generics at all. So when you wanted to write a visitor pattern, it's actually a stateful implementation. It was a bit cumbersome to use. So how does it work? First of all, actually, what do we want to do? So we're going to use only one example tonight. We have an expression, which you have several possibilities for an expression. It can be something that is a numeric, or it can be something that is a sum made of two expressions, or it can be a product, and again, two expressions. So this is a recursive definition. And the problem is, so basically, how can you encode that, and then how can you actually traverse the expression, and you don't really know what it is exactly, so that you can do something with it, and you don't want to touch actually num, sum, and prod every time. So when you are in Java, for example, you only have inheritance in order to encode that. So the basic idea is you have you encode X as being an interface, an abstract class, something like that, and then you have three concrete implementations. And then you want to provide one handle, one function, one method actually in this expression interface, so that you can do something with it. And the kind of things you want to do is, for example, you want to traverse the expression so that you can evaluate the expression, or you may want to print it, or you may want to do any kind of operation, but you don't really know what kind of operation beforehand. So you need something to traverse the expression. And the way you do that actually is with the visitor pattern, you just provide one method that will accept your visitor, and the visitor will just be given the authorization to go through the expression. So basically, this is the visitor for the expression. You have three methods, one for each case, so the num, sum, and prod. And here the unit is important. In this version, this is actually the stateful implementation. I guess everybody can read what's on the screen. Tell me if there is any problem, and of course you can interrupt me at any moment. There are only 5 files, so we have time to speak about them. And then what happens is the expression will say, I have a method to accept a visitor, and so do have all my concrete implementations below me. And this is actually a bit boring because the code will look the same in every implementation, but there is actually something a bit different with all of them. I will go into in detail, but here in this, I would like just to point out that all of them are actually different. They don't have the same type. So in this case, this is a num, this one is a sum, this one is a prod. This is why, and this is how actually you call the right one. So how does it work? The accept says, okay, if I have a visitor here, I actually will give him the right to know everything about me. This is the way it works. So this is basically you you give the control to the visitor to access what's inside. And then you can do whatever you want. This is very simple as an idea. So for example, if you want to implement an evaluator, and here again we need a state, so this is the purpose of this result variable. You can say, okay, in the case I'm visiting a num, I just want to set the result to the n that is within this num. If I'm visiting a sum, I will first visit the left part of the sum, so this one, and I will take the result. I do the same with the right part, take the result, and then I set the result as being the addition of the two calls. And I do the same for the product, but here, of course, I do the multiplication. So that's a very simple implementation, and just for easier use. So in all the examples, I will write just an eval function, taking an expression, computing an int, and I have the main, so you can actually execute that. There is no real test suite, but it's already good enough. So the way it works at the end is, okay, you want your eval. So here, having one eval per evaluation is important because of the state. And then you pass the evaluator to the expression through the accept method, and you read the result at the end. So that's the most boring implementation tonight. It's actually not satisfactory at all, and this is what people were doing a long time ago in Java, before they had the generics. So is there any question right now for that? So what's really important is to understand the purpose, and then we have other examples. So now I would like to give you the Scala version of that, where actually you have a totally different approach based on pattern matching, and much easier actually. So in the case of the pattern matching, you are in a closed world. I mean, you are able to say that your expression knows everything about the subtree, about the none, the sum, and the product. This is done through the sealed keyword. Actually, in the general case in Scala, you don't really need that because the pattern matching has been extended. But in this case, we're interested in the abstract data type approach, and this is how you encode that in Scala. So you have three case classes. They all extend the expression, and because of that, you know that you can just do pattern matching on the expression, and you have the exhaustivity of the pattern matching, and everything is nice, and you don't really. So you can actually traverse the expression from the outside. This is what is given for free by the pattern matching. So the eval function is just straightforward. It's just pattern matching. You extract your information and you call eval recursively, and it works very well. So I guess everybody is actually comfortable with this approach here. So the really interesting things are the three other possibilities. So what can we do here? Maybe we want something in the middle. Maybe I don't want oh no, sorry, I had to give you the visitor pattern that you can do actually in Java, but using the stateless version, where actually you don't accumulate a state, but instead in this version the visitor will actually express what is computed. So this is why you have a generic here, just to say this visitor can visit, that's fine, but it can actually compute a value on the way. So this is the same version as before, but here you can actually return something and you can use it to do something with it. So same version, but here the accept is polymorphic, and so that you can provide a polymorphic visitor, and here again you provide the type information. And the eval function is much easier in this case, because here you can say that actually this evaluator is actually computing, computing the evaluation of the left part, and you can use it to sum it up with the other version here. So it's really straightforward. There is you don't even have to think. It's really easy to write, and it's actually very powerful. You can do many things with that. You can even reuse the evaluator. There is I mean, the instance here, there is no problem at all. But there are actually some issues with that. So first of all, if you want to do that, you have to prepare actually your expression, your type, to accept the visitor. So this is very intrusive. So you may not be very happy with this solution. Another thing that that is not really nice is we have this this code that is duplicated everywhere. Not really cool. And then the last thing is you need to know about the type hierarchy from the beginning. So you don't have all the nice things from, for example, extended pattern matching in Scala, where you don't really need that. It's not mandatory. You can do other things. So we can try to relax some of these constraints. So first we can say, okay, maybe we don't need this this container for the three methods, because in Scala and some other languages you can actually speak about about these functions without having method contained within one object. So we can say, okay, maybe instead of providing this visitor instance, I can maybe provide three functions, sorry, and do something with it. And then we can say, maybe, I mean, most of the time, even if it's not really very clean, it's a bit dirty, but maybe there is a way for X or something that is outside of the type hierarchy to know the distinction, to have a way actually to see that num, sum, and prod are different. You may think about, for example, type inspection or stuff like that. There is always a way. So what would we look like if we go with that? So this is one solution. So let's have, for example, these three classes. They are class classes, and here we have everything that is interested in this X interface. So what happens here? We say, okay, instead of taking one visitor, we just take the three functions. Each of them to be used in the case, if it's a num, I would like to use fnum, function for num. If it's a sum, I would like to use the other one. And this is exactly the implementation I have here. So for those who are not really comfortable with that, it's really, you should read that as, if num is of type num, then the value of accept is that. If sum is of type sum, then this is the value of the expression, and so on. So here, so this is not really clean, because we're using is instance of in a way, but this is not exposed. So in my opinion, this is actually pragmatic, and it can be actually just okay. So this is how you use it. So you just have to provide three implementations, and it looks actually very familiar. You are very close to the syntax of the pattern matching here, and you just use it, the same way. So as a remark, actually, if you rename this accept method and you call it fold, maybe you have seen that in the Scala library. You have some folds everywhere. You have what some people, I mean, not some people. This is what we call a catamorphism. So this is very nice name, but actually it's very easy. This is just the process of giving three functions. In this case, giving functions so that you can traverse the expression knowing all the cases. And every time you find a fold, this is exactly the same thing happening. So yeah, so you find more and more fold methods in the Scala library. You have a lot of them in the Play framework if you use it. Yeah, so that's already a good remark. but there is still, an issue. Okay, you know a lot about these classes, and there is something cool because you can actually compose them in the way you want. You can even break the hierarchy. You can do pretty interesting things. You can provide different way to visit the expression. But sometimes actually you don't have access to the classes. This is actually that was actually the problem I had that made me think about other stuff. I was working on a library to do link data and RDF and stuff like that. There are two main implementations, one called Jenna, one called Sesame. And of course, they don't share anything, but everybody wants to use them. And in my case, I wanted to be able to switch them very easily. And also, I wanted to be able to traverse all the type hierarchy, which is actually pretty complicated. It's much more than 3 cases, and you have different levels. So basically, when you want to do that, you want to use a type class. So that's the way you want to inside without having the type hierarchy and inheritance. But I still wanted to propose a way to traverse the type hierarchy, and this is where actually the catamorphism is used. So what does it look like in our case? So you actually start by defining a module, which in this case you don't really need to. You see that there is no need for an instance of the module. We work at the type level. So here, this is just a way to encapsulate 4 types, and you say, okay, please bind them to some other types in the future. But with that, actually, you have no operations that you can do with them, because when you have the module and the types, well, you are a bit lost. So this is why you can actually provide a type class for it, and this is where this is where you encode your visitor. So we need 2 kind of things. So here you recognize the void. Okay. So we suppose that we have actually a module here. So this is where you have a subtype. You can see that we never compute with n in this implementation. There is no n instance anywhere here. But we actually refer to the types that are encapsulated using the type projection. This is the meaning of the hash. So given an n, here I'm speaking about the num that is referred within this n, within this module. So in this case, I'm saying, okay, if you give me an expression of type, the expression within the abstract module, and if you give me the 3 functions, I can do something with it. That's exactly the same version as the accept method in the previous version. But this is not enough. So here we are just assuming that the implementation will be able to make the distinction in some way. We don't really need to know how at this point. We just hope that it's possible. And of course, it's most of the time possible. But here, if we have a num, we need to do something with it, and we have no way to access the integer that is encapsulated in this num. The same way, if we have a sum, we need a way to extract the 2 sub expressions, and this is where you have that. So you know that. So I don't know if you know that. I was speaking a bit earlier about the generalized pattern matching in Scala, and actually every time you write this match something, and you have case an object and something, so it's referred to extractors. This is actually referring to an unapply method provided to the object. So yeah, let me give you an example, because most of you are here. So you have something you want to match. Here you give a case, and you have, let's say T, and we have T of A, and we do something with it. So the way it works, actually, Scala, we try to find an object will take the implementation, the instance T. So there is no magic there. So this is actually an object, I can refer to it. And Scala will expect that T will have an unapplied method that will take this guy. So you can give it this guy. And Scala will try to extract something from it. So this is basically an option of what you want to extract. So the type of A. So how does it work? So Scala will see, okay, I have this unapplied method, so I can apply it to I can apply the unapplied to that. I can try to extract something. If it works, by convention, this is because I have a sum. And if it doesn't work, this is just not, and I go to the next case. So in our case, we just want to do exactly the same thing. So we say, we want a value that can do exactly the same thing. And we will call it none, because it's very convenient in our case. We have none the value, and at the same time we have none the type. So they share the same name, so it's very convenient. And this instance have only one method, and this is the unapplied. So we suppose that with a none, I can try to extract what? An int. And here the same from a sum. I hope I can extract a tuple of expressions. And same for the prod. I hope I can extract a tuple of expressions. And that's all, because if I have that, now I can write this eval function using the type class. So how does it work? So first of all, we don't want to say what is the module. We just need to know that this module actually has a visitor. That's the only thing we need to know about it. If it has a visitor, it means that I have my fold method, and it means that I have my extractors for the num, sum, and prod. So, nice thing about Scala, you can actually import everything that is in the scope of an instance, so that you can use it right away. So now I have the fold coming from the visitor here, and I just need to provide three functions. So remember, the first function is the case, this is a num and I'm doing something with it. This is a sum and I'm doing something with it. And I'm using actually this construct, a partial function, so that I can extract at the same time. And here there is no problem. So actually this num, that's the cool thing about it, it's actually this one. This is why I can write it. So I know that everything is safe here. I have no compilation message or warning or anything. It's actually just totally fine. I know that this guy is actually a null. I know that there will be no problem at runtime because extracting this information from the null will work. If the implementation is fine with that. And we have seen this implementation several times in the other examples. So what would be an example for that?
Just a quick question.
Yeah,
what happens
sure.
if because it's an option, right? So
what?
That the unapplied returns an option.
Yeah.
It could be that it's none.
It could be none, but we hope that actually there will be no problem. So the what's expected in this case is it will be always an option.
Well, never. Yeah. When the option is the required type, what you're basically expecting is that it's a yes or none. Because you can't. I don't think you.
So the question is. So I never tried actually, because if you read the documentation, the Scala documentation, it will say I'm expecting an option, but maybe it actually won't because it.
No, I think you need to have the option in the unapply type declaration for the matching to work, but your code will break if it returns none, right?
Yeah. Exactly.
Okay,
that's totally right. So it's actually it's your. You have to be careful, and of course you need to be able to map any num to a sum. It should work all the time. Yeah, there may be actually runtime issues if you don't follow this principle. So let me give you an example of that. Let's say that you have a fake expression type hierarchy coming from somewhere else. This is actually just exactly the same thing, just a prefix with fake. They are not case classes, but you have accessors for n, l, and all that stuff. And this is, the module for fake. So here I'm just binding all the types together. I'm just saying, hey, in my case, the expression will be just, the fake expression. No problem with that. And here is my type class instance. So here actually I'm defining the instance none, and at the same time I'm giving the type here, so I'm doing everything at once. So I give the unapply, and here that's really easy. So I know that I have a fake num here, so this is the n. So that's really easy. It's just the conversation we had with Andrew. Just taking the n and I'm returning that in a sum. So here you can see that there is no issue with the runtime. And you do that with everything. You map everything in a sum. The fold is quite easy. So in this case, I'm using again the type inspection, and I'm just giving the right method here. And now I can use the eval method I defined before knowing the implementation. And this works, of course. So I know that this one is a bit more difficult, so maybe you want me to go through it again, maybe you have specific questions, I don't know. And that's very, very useful. I mean, I could do amazing things with that, and so in my case I had, basically type classes everywhere for just to abstract Jena and Sesame, the two main RDF implementations, and I can switch between them very easily, and I can inject the instances of the types at the same time. I can still I have several ways to go through the types. In that case, actually, you see the limits of Java. It's implemented in Java. You have several grammars for Turtle, M3, Sparkle, and other stuff. And they share some stuff together, but they cannot really do it very, very, very nicely because they have only one type hierarchy. So they have actually one very big visitor that has to be used everywhere. And oh, okay, in this case, I know that actually there will be, this part of the grammar will not be considered. I can just throw an exception. I don't have to care about that. And I don't have this issue when I do that through my type class. That's the kind of things I can do.
Do you need to define the fold using the explicit types, or can you also define the fold in the abstract, or in the trait rather, using mnum? Because you define here, if you look at the fold is defined, the types are defined, it's abstract. But the implementation looks like it's going to be the same every single time. The only real difference is going to be that you have to refer to the explicit types.
So this is the implementation.
Okay, so that's the implementation in eval, right? No, it's further down.
So
this bit.
Just speaking about this one?
Yes, yeah.
Yeah, so what's your
I'm just wondering whether you can move that code up into the declaration, and then you can't use fake num because that's the explicit type.
No. So okay, very good question. My first implementation I tried to do that, but sometimes actually you have the types that are exactly the same, and you have to look into the values to decide what is the actual type.
So in other words, it looks like it would be the same implementation every time, but that's not true.
No, it's not true.
Sometimes
so
you do different
one
stuff.
counter example, for example, you can have everything being a string.
You could look at the string.
And you could actually encode everything in one string. So you have strings everywhere. So you need to do something a bit clever. So very good remark. And actually, I hate some Scala bugs because of that. So this code. So there are actually other things that you may want to do. For example, instead of doing a fold, you could be tempted, for example, to use only pattern matching instead of having the fold, and say, oh, I will just define all the unapplies, and I will just hope that it works. And instead of taking here a fake name, I will just take an expression, and then I could just use that in a, the same way in a pattern matching. I wanted to do that for the first time, but actually, so if you read on Stack Overflow, most of the questions about the virtual pattern matching coming from me because I had so many problems with so the previous implementation, but even with the virtual pattern matching, so it works a bit better, but there are some corner cases it doesn't work. For some reasons, for some reasons, sometimes Scala will not take the right T, or will not provide the right type here, and you don't pay attention to it, but actually in your actual implementation, it works not as you wanted, and so it doesn't work. With the third approach, you know that you are forcing the type before you actually extract your information. So I basically did not really know the full trick or anything like that, and I had to invent that myself because I didn't know all the functional programming thing. So very good.
When you're folding a tree, do you not always recurse all the way down the tree?
Okay. So I used the term traverse. Actually, you're not traversing. You are going through all the cases at one level. So traversing is going, is doing that recursively. But the fold is not doing that actually. You are just considering that. Maybe. No.
Well, this fold goes all the way, even though there are only two cases.
So let's say. Yeah, so you are traversing actually. Okay, so I should revise my definition for catamorphism. I don't know if this is the right one or if the one I gave is. Okay, I may have said a mistake about the catamorphism. You should check. In my case, I can. Okay, I'm not sure about that. So, is there any question? I don't know if I lost you or who did actually understand most of the. Okay, a few hands. Okay, so if you don't have any question, I propose that we stop. Thank you.